So where is he supposed to stand? Right in front of the camera?
I'm sorry.
Yeah, he was asking you.
No, and yeah, I guess this part is okay. It's just
Yeah, the camera captures.
capture until
Quite
here.
right. Yeah.
So you can see me now.
Yes, yes. You can even go further if you want.
So this
We can even see Onur now.
Okay, so
So we are like,
okay. Okay, I think let's get started without further ado. It's a pleasure to introduce Professor Ergin, who is a visiting professor at ETH right now. He started in June, right?
Yeah.
Until December, he's visiting EFCL and my group in ETH in general. Oguz is a professor at TOBB. I'm not going to translate the entire Turkish name for it, but let's leave it as Turkish University of Economics and Technology. And he leads a computer architecture group there, and he collaborates quite heavily with us at ETH. And we have quite a few of his students as PhD students, interns, etc., in the group, as well as remotely. He's been there for 17 years. He's also the department chair right now. So he's doing a lot of.
I'm not sure if I'm there now.
Okay.
Momentarily, I might have fired. I'm not sure.
Fine. For me, you're the department chair. But he got his PhD from State University of Binghamton, working with Kanat Ghosh. And we kind of are contemporaries. We met each other at conferences at Micro, I think, maybe 2004 first, if I remember correctly. And he did a lot of work on low power microprocessor design for his PhD, and afterwards he spent some time at Intel Labs in Barcelona before he went to TOBB. And he's been doing a lot of work on processor design, softwares, memory systems, and FPGAs. And he's going to talk about a lot of the research that's going on those topics.
Well, thank you. Thank you for the introduction. Well, TOBB actually stands for Union of Chambers and Commodity Exchanges of Turkey. This is the largest non-governmental organization in Turkey. By law, all the companies in Turkey, they have to be a member of. So this is the richest kind of the NGOs in Turkey. So they established a university, and my joining that university is kind of overlapping with this establishment. So I've been there almost since the beginning of the university. So today I'm going to talk about our research group, Kasırga. Many of our members are sitting here. They're PhD students. So kind of a story of how we collaborate with SAFARI, and some of the stuff is from Barcelona Supercomputing Center as well. So what we have been doing in the last part of the presentation, my MS student, Oğuzhan from Turkey, will just explain our RISC-V processor design, SoC design efforts back in Turkey. So the name of the group is Kasırga, meaning hurricane in Turkish, which was actually the name of the processor that we first designed like 16 years ago for a contest. So it stuck actually afterwards. So today I will talk about 9 papers shortly, briefly, just to talk about, or just give you the sense of what we have been doing, or what kind of stuff that we are doing actually in general. So the first paper I'm going to talk about is QUAC-TRNG. This is a paper of Otabek here. So this is actually his MS thesis, and this actually started with a collaboration when he visited the EFCL, not EFCL, the SAFARI group as an intern, and he came up with the idea to generate random numbers inside the DRAM bit cells. So the motivation is people need random numbers, and they need it with a high throughput. So you have to generate them fast enough. And DRAM cells actually seem to be a good place where you can do these things. And the idea is quite simple: to turn on multiple rows at once, to just share the charge on a bit line, and you can actually get some kind of a randomness, and you can get as high as 3 gigabits per second on the average as a throughput. So before going into the details of the scheme, I just go over how the DRAM works. Everybody knows probably here how it works, but so in the DRAM chip, you have these chips, banks, and maps, and everything, but in the end, it comes down to this one capacitor and one transistor, and there are many of these things. And this has been the same for quite some time now. It is the same one transistor and one capacitor design for a long time now. So you just have the word lines and bit lines. You activate the word line. Before activating, you just pre-charge the bit line to VDD over 2, and then you connect the capacitor to the bit line. There is charge sharing through capacitor to the bit line, and then through the difference, there is a voltage difference in the sense amplifier. Understand the difference, and you can just read it fast because the small capacitor is not strong enough to actually drive the whole line. It is necessary to use an analog device like this to actually sense the bit line. And you just enable, read the value. And this is also not new, it's very old technology. So you have these sense amplifiers, and you have this DRAM command sequence where you just activate, read, and then you pre-charge, and then activate some other line and read. So this is how it works in general, the command structure. And you have all these timing parameters that you have to obey in order to have a safe reading operation. So in order to implement Ataberk's idea of just generating random numbers to activate 4 rows at once, you have to violate these timing parameters. You have to just try to access it earlier than you're supposed to be accessed. And plus, the other observation here is that we have the variations, and not all cells are equal. So they're just different. The charge that hold are different. Whatever parameters that you have on these transistors are different. So the charges that they're shared is going to be random, kind of, for us. So if you just connect 4 of them to the same line, the charge will read, will have some randomness. So when we access it, you'll get, in some of the bits, you'll get some random numbers. So actually, the thing that I want to emphasize here is that this is a very simple idea, and on a technology which is quite old. But in order for Ataberk to actually get it done, he had to go through the process of just kind of reverse engineering how the DRAM works, so that you can actually activate 4 lines at once. You can just tell everybody that let's just activate 4 lines at once and just try to get some random number. But of course, in reality, there are some constraints. You cannot just turn on all the rows at once. You have some constraints. You can turn on this block at once, but you don't turn on actually some of the blocks together at once. So if you try to activate these lines in this order, you can activate 4 rows at once. That's the reverse engineering that Ataberk had to go through, probably with pain. But then, if you can access it this way, then the numbers you read from the sense amplifiers have some randomness in some of the bits. And if you cannot identify those bit locations, you can get a lot of random numbers. And also, another thing that the randomness depends on is what values you store inside the capacitors in these bit cells. So if the number you store is like this pattern, because you have 4 numbers, if it's 1, 0, 0, 0, you have this kind of a possibility that entropy that you get this random numbers. So it turns out that this 0, 1, 1, 1 has the highest entropy. And when you store 0, 1, 1, 1, because we turn on the 0 side before the others, you actually get more random numbers to this. So in the end, this is one paper technique that generates random numbers inside DRAM cells by just turning them on at the same time, 4 rows at the same time. And you can achieve high throughput of random numbers through this. The second paper that I will talk about is Nisa's MS thesis. Well, of course, you generate all these numbers, random numbers from DRAM, but how are you going to design an end-to-end system that will make use of these random numbers? Because who is actually accessing these random numbers, and in what order? What kind of applications require random numbers? And some of the applications, they don't require random numbers. So if they just try to access the memory at once, what will happen? in between them, right? So what are the troubles here? So you have to actually sustain some of the things. You have to keep up the throughput, and you want to actually reduce the interference between the applications that you have trying to access memory while you're generating these random numbers. So here you have to balance three things: the interference, the prioritization, and the high latency. You want to have low latency TRNG, but meanwhile, while you're trying to have low latency random numbers, you want all the other applications that try to access the memory to not suffer. So this paper is mostly about just trying to balance them all and trying to propose some end-to-end solution for people who will try to make use of the DRAM-based random number generators. So for the memory controller, if you have a non-RNG app, this is how it goes. If you have an RNG app, they may overlap. So you might, when you try to concurrently run them, you might have this just back-to-back execution, and some of the time you may actually have high TRNG demand, or you may have multiple DRAM accesses. So there might be some interference. So what the solution is, when you have this whole big stalls, when you wait for the random number for a long time, this might be a bad thing. So the solution is you just put a random number buffer. So you buffer, you just generate random numbers whenever you can and just put it on your random number buffer. But when are you going to activate or fill in this random number buffer? You don't want to do it all the time. So you want to make sure that the DRAM access is idle. Whenever DRAM is idle, you just use it to generate random numbers and fill in this buffer. So we use a predictor to predict when this DRAM is going to be idle, because it has to be idle long enough to allow us to generate random numbers and fill in this thing. If it's going to be short idle time, it's not worth going for the random number generation period. So this is one thing. The second thing about the priority, you have the OS, you have to rely on OS to prioritize between the non-RNG application and the RNG application, because you don't know, maybe sometimes they want to prioritize RNG generation, maybe some other time they don't want to prioritize it. So the OS has to actually help, and you just schedule. You have two separate schedulers in this design for RNG applications and the non-RNG applications, so that they don't interfere with each other. So you just leave the prioritization to the OS. And this paper also provides an API so that you can just use this whole system. So that was Nisa's MS thesis, and it got published in HPCA 2022. Also, Atabak's paper was published in ISCA 2022, right? Or 21? 21. So in order to implement,
I have a question.
Yeah, sure.
Why do we need random numbers?
Well,
random numbers.
Well, that's a good question. Well, everybody tries to motivate this, right? So the cryptographic applications or whatever people need for quantum computing, people need a lot of random numbers. But what happened for us was with Ismail's thesis, I'll explain. One of the Turkish professors in California, they were working on this p-bits, which were just trying to simulate quantum computing with regular SRAM bit cells. So when you try to do something like that, you need a lot of random numbers, and actually throughputs even higher than what we can provide here. So we provide like 1 to 3 gigabits per second. They require like more than 100, right? It's something like that. So there are some people who are looking for these random numbers, and when they found us, they actually wanted Ismail to join them just to generate random numbers for them. So it is on high demand so that they can actually fly people to US to actually generate random numbers for them. But there are some applications which require high bandwidth of these numbers. But I think there is one lack of thing here, which is a benchmark suite. We don't have a benchmark suite that actually shows the applications that require these random numbers. So if we had that, it will be easier to answer this kind of a question. But yes, it starts with the motivation saying that there are these applications exist, and we had our own experience that some people wanted this kind of designs from us.
Do you think, is it possible to generate random numbers with a particular seed here so that you can reproduce the result?
Well, in the end, we don't actually use any seeds. We just get the values from the DRAMs. But whenever you use in NISA's design, this end-to-end design, whenever you use a random number, you just delete it from the queue. So one random number is not used twice, so that you just don't, you try to make it as true random number as possible. So these are called TRNGs, true random numbers. Well, there is a definition of this, but of course, in the universe, I'm not sure if anything is truly random. But no, we don't use any seeds. We just use the inherently randomness of this variation-based data that comes from the DRAM cells. Yes.
So
Thank you. Thank you.
another question. So we activate multiple rows in DRAM to generate random numbers in QUAC-TRNG, right? Can we, does this principle apply to other memory technologies as well? SRAM arrays, for example, can we do it in the caches?
Yes, I will talk about that in the end. This was Ismail's semester. So
Okay.
there is some kind of a coherence of this presentation that explains it. I them together. So I'll just proceed if. So when you have these kind of ideas, you need some kind of a tool that allows you to do the experiments on the DRAMs, the real DRAM chips. Actually, this story started with Hassan like 8 years ago when he was the first intern that we sent to Safari group. He had this charge cache idea. He had this idea of just when you access a line, since you refreshed it recently, if you access it again, it's going to be faster. So he had this idea. But at the time, these old people, when they were trying to implement a scheme on DRAM, it was very difficult because they had to code the whole thing on Verilog. And all the accesses, everything, they had to code it. So there was no such tool to just give some kind of an abstraction to make it easier. So Hassan decided to just go for some kind of a scalable tool. It was called SoftMC, was published in HPCA 2017. But after like 5 or 6 years when it passed, it got older. The technology got older. It had to be renewed also for Rowhammer kind of problems when you try to access the DRAM quite frequently. The buffers inside the FPGAs was not enough to hold the code that you wrote for this SoftMC. So we need a new tool. So because you have to generate a new tool, Atabak decided, okay, so it's now time to actually generate a new tool to do these experiments, and DRAM Bender came into the place. So this how it works. You probably know this works with DDR4. SoftMC works with DDR3. So this is an upgrade on that. So people were kind of expecting, because they asked me the question when I went to Georgia Tech. They were looking for some tool to do the experiments on DDR4. And this is a more scalable, more flexible solution than SoftMC, than its predecessor. So many things were changed, but this is a good example when you look at the code. In the old version, there were no branches. So if you wanted to send some commands to the DRAM structure, you had to write the comments all for each line. You have to write them. So you had to write a long code, like 2,000 lines of code. Since you didn't have any for loops, any branch structure that you could use. So this one, DRAM Bender, has the looping structure that makes it easier. Also, the instruction set is different. Now it allows you to use many more instructions than it was used before. So a better instruction set, DDR4 compared to DDR3, also allows loops, and of course makes it easier for the people to do just explore some things to do in DRAM-based research. Of course, these are tools, these are not goals. People, they don't want to do the tools, but in order to reach your goals, you have to design these tools. So this makes it easier for many people to, it's not archive anymore, it's now published in TCAD 2003, this year, right? So there is another tool that Ataberk was working on. So this, we never did something on, or collaborated on something on processing in memory, but many people have different techniques to actually have some acceleration done in DRAM. You have to do some operation in DRAM. So in order to make it possible to explore this kind of ideas with a more end-to-end kind of approach, because you can test it yourself through your very low code or controller, but you want to have it on your software level, just to call a function to see how actually fast it performs, right? So how much speed up you get. So in order to simulate the whole thing, there is a system, there is a RISC-V based CPU core that actually deals with this operations that come from the top level. And you issue DRAM commands to the memory so that you can just emulate, not emulate, but do the whole operation, and meanwhile you can just simulate your own idea in the middle. But of course, you have to write enough of HDL here in order to implement your processing in memory approach. So row clone was actually tried in this paper. You can check it out. So it actually shows some real, I think real speed up numbers, so which were not possible in the beginning. Prior to this paper, it was not possible to show this kind of numbers, to show a end-to-end solution to show the results of a processing in memory approach. So far this was DRAM, and our other collaboration is with Barcelona Supercomputing Center. Ismail visited Barcelona, I think 4 years ago, 3 years ago, 4 years ago, I think, 4 years. So when he was there at the time, you know, there is this AI accelerators. So people try to accelerate AI, the CNNs and DNNs, they want to accelerate them. And the easiest hardware structure that you can use is the FPGAs. And you can just design your accelerator using an HDL, just synthesize on the FPGA and use it. But then it consumes a lot of power. So in order to reduce the power, they want to reduce the supply voltage. But when you reduce supply voltage, when you do undervolting, it's called the undervolting. When you reduce supply voltage, then there are some faults occurring on the FPGAs. So there is actually a trade-off between the power and the accuracy of the AI accelerators. So when you reduce the voltage, it consumes less power, but then there are more faults, so you actually get less accuracy. So there are many works like this, but the first work that we did was trying to actually show this trade-off between the two and trying to optimize it, because in some parts of it, if you just try to map it more intelligently, you can actually get a lot more accuracy. So while we were doing this undervolting studies, there was another question. So we are undervolting these FPGAs, but are they dependent on the environmental effects? If you just increase the temperature, like we're increasing the temperature now in this room, so do the faults occur, or what is the effect of temperature on undervolting? So the regular reliability tells us that if you increase the temperature, the components, they get less reliable, so there are more faults in a regular, this kind of a chip. If you increase the temperature, then there are more faults. But interestingly enough, if you increase the temperature, actually there are less faults in undervolting. But this was a surprising thing that we observed, because when you increase the temperature, since the circuitry operates slower, it is harder for it to latch faults into the FPGA. So you start to see less fault. So actually, it makes sense to heat up your circuitry if you're doing undervolting with an AI accelerator. So you can actually see on the graph that it is possible to undervolt more if you are increasing the temperature. Also, humidity shows the same effect because when you increase the humidity indirectly, you're increasing the temperature as well. So this paper that we have in IEEE Micro in 2022 shows these results that it's interesting enough, when you increase the temperature, the fault rate actually decreases. Yes.
Could you elaborate a bit more on the physics side of this story? Like when you increase temperature, what actually happens to cause those errors? Like what kind of?
Well, we don't know for sure, but because we don't know the circuitry of the FPGA, but we think that because these flip-flops and latches, they actually work a little slower. When there is a fault, it is probably harder for them to latch the fault. You know, there is this masking effect when you have the fault. Sometimes you just create a bit flip, but it doesn't latch correspond to an error. So we believe that because it is slower, they kind of mask the error, but we're not sure. So this is the explanation that I have.
Okay.
But so I also heard about inverse effect of temperature, that when we are in undervolting, that when we actually increase temperature, the circuit operates faster when we are in undervolting. Is that the reason, or?
I don't think it works faster because when you undervolt something, you also decrease the frequency as well because it's like the voltage frequency scaling. Because the delay is actually they go worse than it was before. So when you're undervolting, it is not faster, it's slower.
So no, so we undervolt and we are in this condition, but in that condition, when we increase the temperature, can we operate faster or not?
We don't operate faster, but there are less faults. So that's what we observed. This was a long effort by one of our PhD students, Ergin. He spent a lot of time in the ovens trying to bake these things and then come up with these graphs, and we observed that the faults are actually less than it is before, but it's not faster, it is slower. Yes.
This is a very interesting trend from, but I can see these values go from 20 to 50, 20 degrees Celsius to 50 degrees Celsius.
Yeah. 80 actually, something or yeah, something like that. 50. I don't remember the exact numbers now.
Is it 50 degrees Celsius or 50% humidity?
No, there are some 50 degrees Celsius here with 70% humidity, 80% humidity, so you can increase. There are some just different levels of humidity with different levels of temperature. We also had some experiments with higher temperatures also, but they're not here on this graph.
That was exactly my question, that would this trend continue if we go to like 110 or 120?
Well, it stops operating after some time.
Yes.
Because once you just try to go that, the circuit stops operating.
And why is that?
Because you undervolt, and from after some time, it's so slow that you don't actually latch the correct numbers. Right? So it doesn't work.
Despite higher temperature.
Yes, it doesn't work. So there is a limit of things that you can do here.
And what about like on the opposite side, from instead of 20, maybe we look at -10?
I'm not sure. I'm not sure if he checked minuses, but of course, if you make it cooler, it's not going to get better in this aspect. Well, the observation here is just increase the temperature and you get less faults. And actually, it provides you with some opportunity to undervolt even better. But of course, when you increase the temperature, you also have more energy dissipation because of leakage. So it's kind of contradictory, but in the end, this is the observation. So when we were doing this undervolting stuff, everybody was assuming that the fault distribution in the AI accelerators, it was random and uniformly distributed. But Ismail was working on this, and we observed that it's not uniformly distributed and it's not random. So because you don't want to all the time just generate your own DNN accelerator, put it on an FPGA card and try it out, it takes a long time. You want to know your accuracy before doing this. So people were just trying to come up with a model which was random. Before they did the simulation, did the actual thing, they can get some accuracy numbers. But those uniform distribution assumptions were not correct. So Ismail's actually Morse model shows that the faults are not random. They are not totally random. So when you have the faults in one location, we have this setup. When you have the faults in some locations, there are some kind of a constraints here. So you have a number of bit faults in a row, in a column. When you have a fault in one location, there is the probability of having a fault close by actually differs. It's not a uniform distribution of faults. So if you actually use the same data that they use for this uniform distribution, but try to actually make a sense of it, come up with some rules from it, you can estimate your accuracy better. Actually, the outcome of this model shows that here. You can estimate it 3 times better than this uniform or random modeling of the faults. This was the outcome, and it was published in TCAT in 2022. This was a modeling paper. Actually, people who do undervolting stuff, they better actually use this kind of a model to get a better sense of their accuracy. So afterwards, since we were doing all this SRAM-based undervolting, and we did some DRAM-based random number generation, we were doing undervolting and getting some faults, we thought, why not try to use them both and just try to get some random numbers from SRAM circuitry, which was the question that I asked. So we tried to undervolt the SRAMs and see if there is enough entropy to generate random numbers, and we observed that yes, it is possible in the FPGAs to generate a lot of random numbers and in high throughput. Why is this important? Because on-chip memory is usually SRAM. DRAM is not on-chip. So it is possible to use caches, registers, whatever SRAM bit-based structure inside a chip to generate random numbers whenever they're idle. And we know from past experience that in the cache, there's a cache scheme that actually tries to reduce the voltage to save cache energy. Now it is possible, what we argue, it is possible to use those areas of the cache for random number generation. So these are the papers that I wanted to talk about, and this just outlines what kind of research we've been doing. This is not published yet. It's in some archive. Hopefully it will get published soon, because Ismail went through a lot of trouble to get a lot of numbers for this scheme. Hopefully it will get published soon. So now I will leave the floor to Oğuzhan, and he will talk about our RISC-V based processor and SoC designs. Oğuzhan, can you hear me?
Yes, I can hear you. Can you hear me well?
Yeah, we can hear you well. Can you control the presentation? Let's see.
Yes, I can.
Okay, then.
Maybe we should put Ozan's video, right?
I have the camera on, but can you see me? Okay.
Yeah, wait a second.
Just wait a second. This doesn't change anything on YouTube stream, right?
No, it doesn't.
That's huge. Yeah. Maybe this is better.
Okay.
Doesn't cover the slides.
Shall I start?
Yes, please.
Okay, thank you for the introduction. I will talk about our RISC-V design efforts in Kasırga to follow up with the research. So what we do, we generally design cores in industry demand or competitions. These projects have certain requirements in area and performance constraints, security and licensing concerns, and require reusability between different environments. To create designs to tailor these needs, we create custom-made, original, and adaptable RISC-V cores. So at Kasırga, we currently have 7 up-to-date projects in rough planning order in this table. So K0 is our first RISC-V project. We designed this to familiarize ourselves with the RISC-V ecosystem. Then we moved on with the K0.1. After we finished K0, the Teknofest chip design competition started to be held in Turkey. We designed K0.1 to participate in this competition and created an RV64-IMCX RISC-V core. In the following year, this competition was held again, and we created 3 separate teams and joined with 3 separate designs with RV32-IMCX cores. As we finish those designs, we are currently designing the K1 core. This is our Linux booting processor target. After finishing the earlier designs, we noticed that the bare metal ecosystem is starting to be an issue, and we would need to eventually support some sort of operating system in our designs, and created this project to implement the privileged ISA. As for the future projects, we have the K2. As we are in the later stages of the K1, we realized that we will eventually need more horsepower. So we have K2 planned. It will be our first out-of-order core, out-of-order RISC-V core designed in Kasırga. So I talked about the Teknofest chip competition. I would like to give like a brief introduction to this competition. So it is a RISC-V processor design competition held in Turkey. The goal is to design and implement a bare metal RV32 or 64 IMCX SoC within 6 months time frame. The X extension here is for cryptography and CNN acceleration instructions. They also require the system to include several predetermined peripherals. For example, for 2022, they wanted us to have UART and SPI in our designs. So at 2022, we participated with a single team to this competition and won first place with our first K0.1 core. And in the following year, this year, we participated with 3 teams and got the first 3 awards with our Kasırga, Kızılgök, and Gün cores. After finishing the competition, as I outlined in the table, we started our K1 core. This is our most advanced core to this date. So it is an improved version of Kızılgök and Gün cores. It has a 7-stage RV64 IMCFD extension RISC-V pipeline. It implements the US and M privilege modes, which is the privileged ISA. It also supports the SD39 virtual memory that is also required for Linux booting. The current status of this project is that we are finalizing our virtual memory implementation and starting both the virtual memory tests and boot tests. With these cores, we also develop and maintain what we call the Kasırga system on chip. So we have like many cores, but to allow easy access and usability and extensibility to these cores, we require some sort of common system, common floor to integrate these into. So Kasırga SoC has interchangeable Kasırga cores. This part supports any of our designs that I talked about earlier. It has configurable caches, both in size and associativity or the replacement policy. It also has an extensible peripheral bus that users can connect their memory mapped peripherals to. We provide by default UART, SPI, and PVM modules out of the box. Users can choose to integrate or remove these to their designs. And at last, we have the AXI4 system bus that is an off-chip that is for off-chip main memory requirements. With this, I conclude my RISC-V processor talks. Most of our cores are open sourced, and you can access them through the links or the QR codes. Thank you for listening to me.
Okay, thank you, Osman. So I'll just move this out, right? So this actually concludes our presentation. So there are some other papers that we published in the recent years on security and hardware trojans. We had a Unix security paper, some TRBLSI papers. Also, this year we had a European Testing Symposium hardware trojan paper, but I don't want to go into their details today. We never have PhD students. We usually have worked with MS students and undergraduates. So we train people on design on HDL, some research-based tools. They just learn through developing the tools, and they come up with their own ideas while developing the tools. So this is Kasırga, and this is what we have been doing. So thank you for listening.
So for the RISC-V course that you're working on, do you have what kind of plans do you have for implementing speculative execution? Did you start working on that?
Well, our goal is to actually run Linux on this. So currently we are trying to run Linux on the new version. So in order to run Linux or get a better performance, if we have to go out of order, we will. But going out of order is more complicated. So it makes everything more complicated. So we are going step by step at the moment. Our core marks scores are not that bad because we've been doing for the last 2 years, and Ataberk also worked for this. You have some code in this first one?
K0.
In K0, Ataberk has some effort, and then Ismail, Nisa also worked on the K1 versions, the other K0 version, and then we moved into comparatively, we just try to develop them with 3 separate teams, 3 separate designs. Actually, the teams were competing, so they didn't share information with each other. So now we are trying to just combine 3 of them into one core that runs Linux. So our goal is to have an SoC which actually runs a real computer. Real computer. If we can have a GPU as well, something like an SoC that will be a total computer.
But it can be a slow one.
Yeah, in the beginning it can be slow one.
Okay.
Then we'll see if we can make it out of order. Because when you start to make things more complex, it's very hard to debug, especially at very low level. And we don't have all the resources in the world to actually buy those expensive tools. So
yeah, I just asked this because there was a national power boundary execution on there.
So that's the goal.
Okay.
That's not yet.
So we saw 2 types of random generators. We saw SRAM-based and DRAM-based. Now, I'm not an expert in crypto, but sometimes we run these crypto algorithms that we run numbers, especially in SGX. So is there any problem, like what is preferable between generating using SRAM versus DRAM for crypto workloads?
Well, in terms of the workload, they don't care how you generate random numbers. Right? You can also do other stuff. You can just put in hardware, run some counters, run some temperature-based things, because there are many ways of generating random numbers. It's not, you don't have to use DRAM or SRAM-based. But if you want to have something high throughput, then these come handy because the memory way of accessing memory is already fast enough. So you have a large memory, so it is easier to get some high throughput numbers from memory. So crypto applications, they couldn't care less how you generate random numbers. You can do SRAM, you can do DRAM. It depends on your application, the infrastructure. Okay.
That's kind of one.
Okay.
So I couldn't quite get the details about how you design the memory subsystem with this RISC-V course. So is it just like you're using some plug and play cores, or I don't know if it's
well, for the competition, they are actually giving us a wrapper. So
okay.
that kind of handles the memory operation, and we are not very happy with the wrapper ourselves because sometimes it's not very realistic, but we are going with their version.
Yeah.
But for our purposes, of course, we'll have to improvise on how to do the memory.
Yeah, as you know, there are a lot of different design choices you can explore in the cache hierarchy and the memory controller notation.
We actually went through a lot of things with the cache hierarchies. These have different cache hierarchy choices.
Okay.
So we experimented with them, but currently since we don't have a fully working system, I will say that we resolve this. So,
I assume there's no prefetcher yet.
no, of course not.
Okay.
Poor guys, and if I tell them to just put a prefetcher, it will take a lot of time. We want to get it working first. Once it gets working, and then we can just add some prefetchers, those fantastic things that you can try.
Can you elaborate on the performance comparison of true random number generation by SRAM and DRAM? Do you think if SRAM is faster than DRAM,
No,
why should we do using DRAM?
well, DRAM is 3 gigabits per second in our implementation. In SRAM, it's 1.5, something like that. But of course, in SRAM, if you put more FPGAs, I guess you can generate a lot of numbers. It's like a scalable solution. That's actually what these guys in California was asking for, because they need 100 gigabits per second. So for them, it's no issue. Just put the FPGA boards next to each other and just generate random numbers. So if you want to generate your bandwidth, it's more scalable solution maybe for FPGA-based. For DRAM, it's also possible. Right? You can put more modules.
DRAM is cheaper.
Hmm? Well, maybe the money is not an issue. I don't know if you really want to.
It's faster and cheaper. So.
Of course, Ataberk favors his own solutions. It also depends on what kind of system you have.
Thank you.
And what is the motivation for SRAM based if DRAM is faster?
Because SRAM based can also be on chip. Because all the memory on chip is currently SRAM based. So you can also do, if you don't need high throughput random number, you can still actually generate them on chip with the SRAMs, which are not used at the time. So that's the motivation compared to the other.
Thank you.
Okay.
I have a question on these RISC-V cores. If you go back to that slide where Oğuzhan listed them, you have some frequencies associated with them.
This one.
Are these like implementation frequencies on FPGA, or are they synthesized?
Or some, which frequencies were these?
Yes, so on FPGA, best of our cores can go up to like 150 megahertz, but we are using OpenLane, and because of that, we are having some like implementation issues. So these are the frequencies for OpenLane toolchain. Since it's open source, it's not that good.
Well, we have to go through the OpenLane because of the competition as well. That's why we have these layouts here, these pictures. These layout pictures are real, that are the outcome of the OpenLane. But I'm not sure OpenLane is the way to go currently to actually produce a chip. We had some trouble. It's still in development phase, and it's very hard to actually do something like this.
So these are not fabricated. These are just.
They're not fabricated, but they are ready to be fabricated. So we can just give it out and just.
But you can probably get much higher frequency than FPGA.
Of course.
And a related question, like in PiDRAM, we use the record chip, right? Have you thought about using any of these cores?
We have to ask Ataberk, do you want to use these new cores?
He's in front of me, so I can.
Actually, some of them, they have quite hard core marks scores. We have some comparison graphs that we showed in the contest. Their core mark scores are not bad. They're not very poorly actually performing cores, especially the one because but of course it's a competition. It has some definitions. You have some way to trick the system to just make it kind of faster. But in a real system, yes, we have. I think our core mark scores are okay.
So what is the I want to learn a bit about competition. If people want to ask questions, they can ask also. They can tell me. This competition, what does it test? Does it test the core itself or the entire system?
It's test the entire system, right? Maybe Oğuzhan can tell because they also test everything. They want to see everything is running. So
yes, in the competition, they test the whole system like as a wrapper. They test the UART and PVM as well, for example, and the caches are also included. So they just take the whole wrapped core, for example, our Kasırga SoC, and they test it with their main memory.
But there are also demo sessions where you show your code, you explain how it works, those kind of things as well. So this is like a 3-day workshop. So these people from TÜBİTAK, this NSF counterpart of Turkey, they come, they are the actually referees of these judges of this competition. So they ask a lot of questions. I guess they use their own RISC-V-based processor design as well. So they test and they ask questions also, and they see the code. Even if you cannot run the code out there, because these were the first 3 contestants that we won everything, but there were some other people as well. It's not that we are the only people that attended the competition. So there were some teams that they couldn't get it work, but they got some mentions in the end. So you can also try to explain and get some points.
So did they check only the correctness of the implementation or also the performance, energy?
Oh, everything. Everything. They actually gave some points. I think there were some multiple judges. They gave points depending on how fast it is, how is the design. Also, the third team that we have, they got some good, how do you say, team spirit, the best team spirit award, because all the team members here, they're undergraduate students. So 2nd and 3rd year undergraduate students. So they were very young, and with very little help, they were able to pull this off. Working processor SoC in 3 months is a big deal. So those kind of awards also exist. Best team spirit, ready to go guys, those kind of things. Okay. I guess it's done. So this was our experimentation of just overheating people to see how many faults occur in your brains. So let's see how it works. Just report the faults that you observe on yourself.
Thanks a lot.